Okay, so this is an adaptive follow-up question from a college-level physics course from Module 10, Oscillations and Waves. It says that a diving board oscillates with simple harmonic motion of frequency 2.7 cycles per second. What is the maximum amplitude with which the end of the board can vibrate in order that a pebble placed there will not lose contact with the board during oscillation? So the first step in my problem solving strategy is that I just simply drew out a very simple sketch of the diving board. I drew little arrows demonstrating that it's oscillating back and forth, and then that dot right there represents the pebble with the force of gravity acting upon the pebble. Then I made a list of known and unknown values. X represents the amplitude, which is a quantity we're trying to find. Frequency is 2.7 hertz, which is the resonant frequency, and the acceleration of the system is equivalent to acceleration due to gravity, which is approximately 9.81 meters per second squared. This is important because if it accelerates any faster than this, then the pebble will start to bounce on the diving board. I also made a list of equations relating to simple harmonic motion. Next, I used Hooke's law to solve for the elasticity constant of the diving board, which is simply F is equivalent to the constant times the amplitude or displacement, and I just used simple algebra to solve for K. Then I used Newton's second law to solve for force, which is in relation to K, which is simply mass times the acceleration of the system over x, or displacement. And we know that the acceleration of the system is equivalent to the acceleration due to gravity. So we can say that k is equivalent to mass times acceleration due to gravity divided by the amplitude. Then I recognized that the period of simple harmonic motion can be related to t, which is period, is equivalent to 2 pi times the square root of mass over the elasticity constant. Well, we solved for the elasticity constant in terms of m times acceleration due to gravity and displacement. So you can go ahead and plug that into here and derive this expression here. We can then use some simple algebra to eliminate the mass of the pebble and come up with this expression, which is the period is equivalent to 2 pi times the square root of amplitude, or displacement, divided by acceleration due to gravity. So then I asked myself, well, how does the period relate to the frequency? Well, we know that t, the period, is also equivalent to the inverse of the frequency. So you can plug that in for t, the inverse of the frequency in for t, and derive this expression here. Now we have all of our quantities known except for displacement, or amplitude. So now we can solve the problem. Again, using some simple algebra, we can multiply by the inverse of 2 pi, both sides by the inverse of 2 pi. We can also multiply by the square root of the acceleration due to gravity to eliminate that term. And we can derive this expression here and square both sides, solve for x. We now have all these terms given by the problem, and we can now solve for the maximum amplitude, which is x is equivalent to 0.034 meters, which is the maximum displacement that the board can be displaced by, with the pebble remaining in contact with the diving board.